Hello, this is Professor Jim Caffey, and today we are doing Chapter 16, continuing with learning about the Sun. And in this chapter, and in the chapters going forward, we will look at the Sun as a nuclear powerhouse. It takes a lot of energy for the Sun to shine, and it will do so for another 5 billion years. The Sun has been shining for a good 4 to 5 billion years already. These two scientists, Kelvin and Helmholtz, Albert Einstein, a young man, in 1912, and Wolfgang Pauli in 1945, considered the father of the neutrino. Maybe you have heard of a neutrino. We will discuss it. Inside the Sun and in nuclear reactions, we have two processes going on. Fusion is combining two things, and fission is taking that big one and splitting it apart. And these both go on. Now, some of this I'm going to gloss over. Some of this is a little too much for an intro class. But one of these steps that we have to generate fusion and heat and energy in the Sun is what we call the proton-proton chain. And basically it is taking some hydrogen and smashing it together and forming a more stable elemental hydrogen, and in the process we get some other stuff, including the neutrino. In another step of this proton-proton chain, we take the stable hydrogen and the elemental hydrogen, smash it together and get helium. And in the process of doing that, we get a gamma ray energized, high energy. And the next step, we take the helium and we smash it into a more stable process of the 4-part helium atom. We get some hydrogen coming out. In the Sun, we talk about gas pressure. And so you can imagine billions more pressure than under the ocean inside the Sun. What we have in the Sun is a process called hydrostatic equilibrium. In the inside of the star, you have pressure pulling out, taking that energy from the Sun to press it outward and expand. But gravity in the star wants to compress it. So when you compress that gas inside the Sun, it kicks on fusion and burns more, and that makes it escape and expand. In the Sun and in the most stable stars, we have hydrostatic equilibrium. The two processes are in synergy. They are stable. They are in balance. The two processes are in balance. In the outer layers of a star like the Sun, we have convection. And this is just a process like boiling a pan of soup to bring the hot interior to the outside. Deep inside the Sun, these photons of light are trying to get out. And it's so clumped up together inside the Sun. It's so dense that what we have is a photon inside the core. It takes 100,000 years to bounce around and escape out the Sun to reach the Earth. 100,000 years. It takes a while. Now, a photon, a beam of light, will take all these paths to go through the sun, bounce around. A neutrino, however, is neat. A neutrino will go right through the sun, right through the earth, right through your body, and you don't detect it. We have detectors in the earth, and they are large. These things go through us, and we don't feel them. Now we saw the interior structure of the sun in chapter 15. And to review, we have a core in the middle, the radiative zone going out 2/3, and then the convective zone. And the process by which radiation is moved in these zones is different. We have sunspots and granulation on the surface, on the photosphere. One neat thing we found out about the sun with a network called GONG, G-O-N-G, is to measure oscillations in the sun. And what we have found out is that the sun vibrates about every 5 minutes. It vibrates and it makes these oscillations. You can't hear them in what we hear, but we can put them on an oscilloscope and hear the sounds. The structure of a sunspot is quite complex, but underneath the sunspot, the area of the sun is cool, and there are lots of magnetic fields being put in play here with magnetic sunspots. One experiment called the Davis experiment won the Nobel Prize in Physics in 2002, and what this was to study the neutrinos. We can put neutrinos into chlorine, and I'll show you the next picture here. This is a neutrino detector, and so this sphere has all these imaging detectors on it. They look for flashes of light inside. When a neutrino hits that chlorine, it's going to make a photon of light and it flashes blue or green, and we see that with the detectors. Won the Nobel Prize in Physics. When there is a supernova explosion, we can usually know it pretty quick by our neutrino detectors. So that wraps it up for chapter 16, continuing our lectures on the sun. We'll do more of these coming up in the future. Thank you for joining me. I'm Professor Jim Cathy. Thanks.